In this video, I like to introduce two things. First one is completeness property of R and the second one is nested interval property or nested interval theorem. First, I like to introduce completeness property of R. Completeness property of R. This has two statements. First statement is that if S is a subset of R which is bounded above, that is S has upper bound. That is, if we take any subset which is subset of R and S has upper bound, or we can say that S is bounded above, then completeness property of R says that it has a least upper bound. That is, if we take any subset, a subset of R which is bounded above or which has upper bound, then completeness property of R says that it has a least upper bound. Whenever we take a subset which is bounded above, it has a supremum. Then the second statement is say that if S is subset of R which is bounded below, that means S has a lower bound. If S has a lower bound, then the second statement of completeness property of R says that it has a least upper bound. Whenever we take a subset which is bounded below or the set S has a lower bound, then completeness property says that it has a greatest lower bound, that is S has infimum. Next one is nested interval property. Nested interval property. This is a theorem. Theorem says that if In is closed interval an bn is closed interval an bn, and which has a property that I1 is the biggest set, that is I1 is superset of I2, superset of I3, superset of etc. That is, we have a closed interval In which is a nested sequence of intervals like I1 superset of I2, superset of I3, superset of like this. Then theorem says that intersection In is a non-empty set. Intersection In is a non-empty set. That this theorem is called nested interval property. Okay, we need to prove that intersection In is non-empty. We need to prove that intersection In is non-empty. Okay, and we know that In is closed interval a and bn, and it has the property that I1 superset of I2 superset of etc. And then we can draw these intervals. We can mark this interval like this. I1 is the biggest set, so since In is a and bn, so we can write I1 as closed interval a1 b1, and I2 is a2 closed interval a2 b2, and which is satisfies which is like a nested sequence of intervals. That is, I1 is biggest set, so closed interval a1 b1 is biggest, and a2 b2 contained in a1 b1. So we can mark like this a2 b2 etc. like this. Okay, and also we can mark these intervals like this. A1 b1 is biggest set, a1 b1. A2 b2, of course a2 b2 is inside the set a1 b1, so we can mark like this. This is a2 b2, and a3 b3 interval a3 b3 is inside a2 b2, so we can mark like this a3 b3. Okay, and at last an bn. We can draw nested sequence of interval like this. So also note that suppose I define a set which is a1 a2, sorry, a is n belongs to n is n belongs to n. Also note that every members a1 a2 a1 a2 a3 etc. all an's are less than or equal to b1 b2 etc. This is evident from this picture. That is, an less than or equal to, at least an less than or equal to bn for every n belongs to n. This is evident from this picture. That is, every an is less than or equal to bn. That is, a in particular an less than or equal to b1. That is, the set A is bounded above. That is, the set A the set A has an upper bound b1. That is the set A is bounded above. Then by supremum property of R, which says that A has a least upper bound, that is A has a supremum. A has a supremum since the set A is bounded above. So we can take supremum of A is X. Supremum of A is X. Please note that X is the supremum of the set A. X is the supremum of the set A. And also we know that every member Bn is an upper bound of the set A. And since X is the least upper bound, supremum of the set A, and also we know that supremum of A is X. Since X is the least upper bound, B1, B2, B3, etc. Bn's are upper bounds of the set A. We can say that X is less than or equal to Bn for every n belongs to n. Since every Bn is an upper bound of the set A and X is the least upper bound, so we can write X is less than or equal to Bn for every n belongs to n. X is less than or equal to Bn for every n belongs to n. Okay, we reached that X is less than or equal to Bn for every n belongs to n. Also we know that X is the supremum of the set A. And also note that X is the supremum of the set A. So we can write An less than or equal to X since X is the supremum of the set A. That is An less than or equal to X for every n belongs to n. That is, we can combine these two things. That is X less than or equal to Bn for every n belongs to n and An less than or equal to X for every n belongs to n. We can combine this. That is An less than or equal to X less than or equal to Bn for every n belongs to n. That means X belongs to closed interval A n Bn for every n belongs to n. That is X belongs to closed interval A n Bn is, we represent it as In. That is X belongs to In for every n belongs to n. That means intersection In is a non-empty set. That is the proof.